This is Physics 2120, Lecture 7, and today we're going to talk about capacitors. So capacitors are devices that store electrical charge. And we use capacitors in things like radio receivers, filters for power supplies, maybe an energy storing device like an electronic flash. They're just things that store electric charge for us to be able to use in a circuit. The definition of capacitance, C, is defined as the ratio of the magnitude of the charge on either conductor to the potential difference across the conductor. So capacitance is Q over the potential difference. The SI unit of capacitance is the farad. So what is a capacitor? A capacitor is two conductors, and we typically call these plates. They don't have to be flat, but in a lot of devices they are. And when a conductor is charged, the plates carry charges of equal magnitude in opposite directions. And a potential difference is going to exist between the plates due to the charge. Capacitance is always going to be a positive quantity. And the capacitance of a given capacitor is constant. Now, the capacitance is a measure of its ability to store charge. And a farad is a huge unit of capacitance. Typically, you will see capacitors in microfarad or picofarad range. The simplest capacitor to start talking about and understanding how they work is a parallel plate capacitor. Each plate is connected to a terminal of a battery. And if the capacitor is initially uncharged, the battery establishes an electric field in the conducting wires that will charge up the plates. This field applies a force on the electrons in the wire just outside the plates, and that causes electrons to move onto the negative plate. And it will continue to go until equilibrium is achieved, or in other words, the plate, the wire, and the terminal all become at the same potential. At this point, there is no field present in the wire, and the movement of electrons ceases. The plate is now negatively charged, and an opposite process occurs in the other plate, where electrons move away and leave it positively charged. In its final configuration, the potential difference across the capacitor plates is the same as that across the battery. So if the plates are now full of charge, there is a charge density on them where sigma, the surface charge density, is the amount of charge over the area. And then there's an electric field between those plates. And if I have parallel plates, that electric field is uniform in between the plates and zero everywhere else. We said the capacitance is proportional to the area of the plates and inversely proportional to the distance between the plates. We know that capacitance is Q over delta V. Well, if it's a uniform electric field, then we can use our substitution that the voltage potential in the electric field between the plates is ED. And we can know what the electric field is due to a parallel plate, and that's Q over epsilon A. And so solving, we get the capacitance is epsilon A over D. Now notice that the capacitance only depends on the geometry of the plate, how much area it is and how far apart the plates are, not on the voltage or the charge or anything else. It's purely a geometric function. Now we made some assumptions here. We assume that the electric field is uniform in the valid in that central region, but it's not really true at the end of the plates. And if the separation between the plates is small compared to the length of the plates, we can ignore that non-uniformity at the edges. But if that distance is similar to it, we can see that in this area here between the plates, we see that it's uniform, but when we get right over the edge, we get some non-uniformity. Now, I don't have to have parallel plates for capacitance. I can have many different configurations. So one example is an isolated sphere. Let's say I have a spherically charged conductor. And we're going to assume, as we have in the past, that V equals 0 at infinity. The capacitance is Q over delta V, which in this case is going to be Q over KQ over R, which is just R over K, or 4 pi epsilon naught R. Notice that this is independent of the charge and the potential difference. The capacitance only depends on the size of my system. So let's work out another one. What's the capacitance of a cylindrical capacitor? A cylindrical capacitor is a device. I've got a center conductor, and then I have either air or maybe I have some spacer and an outer conductor. If you've ever seen a coaxial wire, we could use a coaxial wire, for example, to make a cylindrical capacitor. So we know that the capacitance is Q over delta V. Let's assume that the center conductor up here has a charge Q and the outer conductor has a charge minus Q. So the potential difference between the two conductors, which would be VB minus VA, is we can just calculate if we know what the electric field is in that region. So it's minus the integral from A to B of E dot ds. Well, let's assume I've got a linear charge density lambda. It's Q over the length of this thing. I could calculate the electric field using Gauss's law. The integral of E dot dA we said is E times 2 pi RL. We've done this problem. That's equal to the charge over epsilon naught, which is lambda L over epsilon naught. So the electric field in the region between the two conductors is 2k lambda over R, and it's radially outward. So now, I can take this result from Gauss's law and plug it in to my equation for delta V. So delta V is minus the integral of E dot ds, which is going to be minus 2k lambda times the integral of 1 over R dr. I get minus 2k lambda times the natural log of B over A. And we know that C is Q over V. So delta V, we said, is 2k Q over L natural log of B over A. So we divide Q by delta L, and we take the absolute value because we said capacitance is always positive. And the capacitance is L over 2k times the natural log of B over A. Again, notice it didn't matter what charge I have on there or anything else. All that matters is the geometry, the length of the capacitor, and the inner and outer radiuses. How about a spherical capacitor? Let's say I have a centrally charged sphere with a charge Q on it, radius A, and an outer sphere with a charge minus Q on it, radius B. Well, we start off needing to figure out what the electric field is, and we can use Gauss's law again. In this case, it's spherical, so E dot dA is E times 4 pi r squared. And that's Q over epsilon naught, so electric field between A and B is KQ over R squared. Now, we can figure out the potential difference between A and B. It's the integral of E dot ds. So that's going to be minus the integral of KQ over R squared, and ds in this case is dr. And we take the integral, and that's KQ over R, and evaluate it from A to B. You get KQ times 1 over B minus 1 over A. The capacitance then is Q over delta V, which is just the Q's go away. You get 1 over this K times 1 over B minus 1 over A, and we can find some common denominators and clean it up. And we see the capacitance is AB over K times A minus B. Notice again that it only depends on the geometry of the system, not on the charge. By the way, we can see here that A is less than B, so this number here would be negative, so we can switch them and then everything would be positive. So the capacitance is AB over K times B minus A. So we've looked now at how to figure out what the capacitance of an object is. We've talked about some specific examples. But now how do we use it in a circuit? Because eventually we have a capacitor is just a device to be used in a circuit. A circuit diagram is a simplified representation of an actual circuit. We're going to use certain symbols to represent various elements of the circuit. Lines are going to represent wires. A capacitor is this blue symbol here. It's two parallel lines, referring to a parallel plate capacitor. A battery is also two parallel lines, but I have a short line and a long line. The long line is the positive side of the battery. And of course, I could also have other objects like the switch here. It's a wire that has two open lines, and I have another wire that can close to complete the circuit. So, I can hook up various objects in two different ways, parallel and in serial configurations. Let's talk about what parallel means. When I have capacitors or they're connected in a circuit, electrons can be transferred from the left plate through the battery to the right plate, leaving the left plate positively charged and the right plate negatively charged. The flow of the capacitors ceases when the voltage across the capacitors equals that of the battery. The capacitors reach their maximum charge when the flow of charge ceases. The total charge then is equal to the sum of the charges on either of those capacitors. Now, because of the parallel configuration, which remember the parallel configuration said I have one capacitor and another capacitor, and they're hooked both to the same side of the battery. They're in parallel because the voltage across the capacitors is the same in both cases, because the potential of the positive has to be the same on both plates, and similarly on the negative side. So the potential difference across the battery is the same as the potential difference across the capacitor. The total charge on both plates is equal to the sum of the charge on each plate. Well, I know that the charge on plate 1 is its capacitance times delta V, and the charge on plate 2, capacitor 2, is its capacitance times delta V. Delta V is the same in both cases here. Well, let's add these up. So, the total charge is C1 delta V plus C2 delta V. So C1 plus C2 is equal to the total charge over the potential difference. Well, that's just would be the capacitance of the equivalent capacitor. If I were to remove those two capacitors and put one in, I get my equivalence. So the equivalent capacitance of any two capacitors connected in parallel configuration, I just add up the capacitance. So in my circuit diagram then, I can take those two capacitors and replace it with one equivalent capacitor. So I have these two capacitors here, C1 and C2. I can redraw my circuit here and with this equivalent capacitance whose value is C1 plus C2. The equivalent capacitor must have exactly the same external effect on the circuit as the original capacitors. I can have as many capacitors in parallel as I want, and I still just add them up. So the equivalent capacitance of parallel combination of capacitors is going to be greater than any of the individual ones. Essentially what we're doing is we're combining the area of the capacitors. Now the other way we can hook up objects in a circuit is series, where I connect one after another. And when a battery is connected to this circuit, electrons are transferred from the left plate of C1 to the right plate of C2. As this negative charge accumulates on the right plate of C2, an equivalent amount of negative charge is removed from the left plate of C2, leaving it with an excess positive charge. All of the right plates then all have the same charge minus Q, and all of the left plates have a charge of plus Q. The equivalent capacitor can still be found that performs in the same function as the series combination. The potential differences in this case add up to the battery voltage. So I know I've got so much potential difference across the battery. This potential difference, if there's 10 volts here, if there's 4 volts here, there has to be 6 volts here, because the potential difference from this point to this point has got to be the same as across the battery. So I know that the total potential difference across the capacitors is equal to the potential difference across each one. But I know delta V1 is Q over C1, and delta V2 is Q over C2. So I can plug that in. And I also know that delta V total is the charge over the equivalent capacitance. And then in this equation we can get rid of the Q's, and we see that 1 over the equivalent capacitance is 1 over C1 plus 1 over C2. I can do this for however many capacitors I have in series. The total potential difference is just the sum of all of the individual ones. So 1 over the equivalent capacitance is 1 over C1 plus 1 over C2 plus 1 over C3 and C4, however many capacitors I need. The equivalent capacitance of a series combination is always less than any individual capacitor in the combination. Some problem-solving hints when dealing with the capacitors. Be careful with the choice of units. In SI, capacitance is in farads, distance is in meters, potential difference is in volts. Electric fields, remember, can be volts per meter or newtons per coulomb. When two or more capacitors are connected in parallel, the potential differences across them are the same. The charge on each capacitor is proportional to the capacitance, and the capacitors add directly to find an equivalent capacitance. When two or more capacitors are connected in series, they carry the same charge, but the potential difference across them are not the same. The capacitances add as reciprocals, and the equivalent capacitance is always less than the smallest individual capacitor. Now, one problem that we might see is an equivalent capacitance problem, where I need to take maybe this complicated circuit here and find the equivalent capacitance of all those capacitors. And the way you do it is you're literally, just like I've shown here, we're going to draw pictures. And we're going to draw circles around things that we know are in series or parallel. Now, these two capacitors here are not in series, because it's not one after another, because I have this other branch down here. So I can't add this one and this one in series until I do something with these. But I can take these two and say these are in parallel. So I have a 1 microfarad and a 3 microfarad, and I add those. They just add up. And I replace this here with that capacitor. 1 plus 3 is 4. I could do the same on the bottom side here. Right, I have the 6 plus 2 is 8, so I can replace these with an 8. Now I can look at this and say these two capacitors are in series, so I can add them reciprocally. So I have 1 over 8 plus 1 over 8 is equal to 1 over the equivalence. 1/8 plus 1/8 is 1/4. So C equals 4 microfarads. And that's exactly what we've done. We've replaced those two with 4. Up on top, we see we have 4 and 4. So in series, that would be 1/4 plus 1/4 is 1/2. Take the reciprocal, and I get it's 2. Now, we can do this one more time. In this case, these two capacitors are now in parallel. So if they're in parallel, we add them up, and the equivalent capacitance of the whole system is 6. Now we said capacitors store charge, but they also are a way of storing energy. Well, let's look at this system. We have this circuit. We have a battery. It's got some chemical potential energy in it, which I can cause electrons to move. Now, before I close this switch, the energy is stored as chemical energy in the battery. But when the switch is closed, the energy is transformed from chemical to electric potential energy. Essentially, I get a positive charge that would form on this plate and a negative charge on this plate, and that causes a potential difference between the plates and an electric field being set up. The electric potential energy is related to the separation of the positive and negative charges on the plates. A capacitor can be described then as a device that stores energy. So, how much energy is stored in it? Well, let's assume the capacitor is being charged, and at some point it's got a charge, little q on it. That just means it's not fully charged. When it's fully charged, it would be big Q. But little q is the charge at any point in time. How much work does it take to put a little bit more charge on? The little bit of work it takes to put more charge on is the potential difference times the charge. We said the potential difference is Q over C. So the total work then, we're going to integrate when I have zero charge to fully charged. So the integral of Q over C dQ, which is Q squared over 2C. So the work done in charging a capacitor is the potential energy stored in it. It's Q squared over 2C, or I know that Q over C is delta V, so that's 1/2 Q delta V, or getting rid of the Q, I can say it's 1/2 C delta V squared. This applies to any geometry capacitor. The energy stored increases as the charge increases or as the potential difference increases. In practice, there's a maximum voltage that I can have between the plates before I get electrons jumping across and I get discharge. Notice the energy has the form 1/2 something something squared. Right, we've had 1/2 mv squared, 1/2 kx squared. We can remember this as 1/2 cv squared. The energy is considered to be stored in the electric field. So for a parallel plate capacitor, the energy is expressed in terms of the field. U is equal to 1/2 epsilon naught AD times E squared. Or I can express it in terms of the energy density. Energy density is just energy per unit volume. A times D is the volume of space that the electric field exists in. So U over AD is the energy density is 1/2 epsilon naught, this should be in epsilon naught, E squared. So what did we talk about today? Capacitors are devices that store electrical charge. We worked out how to figure out capacitance. We may need to use something like Gauss's law to determine the electric field, and then integrate to find potential difference between two things. And then we have a relationship between capacitance and charge and voltage. We talked about capacitors in series and parallel, how to find equivalent capacitance. And we talked about the energy stored in a capacitor.